Alright, here we go. Here's our first lecture of the semester for Math 140. So chapter 1, so this first part here is just going to be a review and introduction to some algebraic topics and terminology. So there's our objectives there. We can do all kinds of stuff today. Alright, so you'll see in your notes, as long as I uploaded the proper set of notes, that all the red text that I have here, that you will have it blank. So you're welcome to pause this video as you fill in all this information. Let's see, so we're talking about sets of numbers first. So here's some definitions. A set. So what is a set? It's a well-defined collection of objects, including but not limited to numbers. Well, that sounds fine, but what does that mean, right? A well-defined collection of objects. In other words, the set has to be properly defined or easy to understand is what they're saying. In other words, you can say something like all the whole numbers, or all odd numbers, or all even numbers, or all letters of the alphabet, something like that. Okay. Number 2, elements of the set are the members of the set. In other words, they're the items inside the set. So if we're going to say, our set is the vowels, then our elements would be A, E, I, O, U. Number 3, a finite set. Finite just means there's you can either count or easily describe all the values, right? So all the elements of the set can be listed. Then we have an infinite set. So you've heard the term infinity before. It just goes on forever. So in an infinite set, all the elements of the set cannot be listed, right? Like they said. If they said list every single real number that exists, well, you can't even list every single real number that exists between 0 and 0.1, right? There's always going to be a smaller and smaller and smaller decimal. Alright, speaking of real numbers, so we have a few different subsets of the real numbers. So the natural numbers, also known as the counting numbers. So, when you were a little kid, if they said, count how many whatever you have, how many pencils you have, you didn't start at 0, you started at 1, right? So 0 is not a natural number. The natural numbers are the whole numbers from positive whole numbers, 1, 2, 3, 4, etc. And just for notation purposes, whenever you see the 3 dots like that, that just means the list keeps going in that direction. Okay, and you can see this one here, you got the dots before, 3 dots before and 3 dots after, which means these numbers keep going negative and in the positive direction forever. Okay? Alright, just some notation there. The next one here, integers. So integers are any whole number. It includes 0 and negative whole numbers as well. Alright, rational numbers. So think of that word, rational. Look what word is inside the word rational. The word ratio. A ratio is a fraction, right? Alright, so rational numbers, any number that can be written in the form P over Q, in other words, a fraction, where P and Q are both integers, so whole numbers, but Q cannot equal 0, right? Q cannot equal 0 because Q is in the denominator. And remember, there's a term that we use if we have 0 in the denominator, and that term is undefined. Alright, in other words, it won't exist. Rational numbers can be written as terminating or repeating. Alright, so in other words, you could have repeated values on your decimals, and or it can end. The next one we have are irrational numbers. So irrational, the prefix IRR, or IR, sorry, not an English major, I'm a math major. The prefix IR means not, right? So in other words, these are not rational numbers. So they cannot be written as in the form of a fraction with integers on top and bottom. Okay? Irrational numbers can be written as terminating or repeating as well. Alright, here's some examples. Write the following sets in two ways. Alright, so let's see. Part A. Set A containing the natural numbers less than 7. So natural numbers, again, we can look up here, right? Those are your counting numbers. So 1, 2, 3, 4, etc. Whole numbers, starting at 1 or higher. But this one says natural numbers less than 7. So let's, since this is a small set, we could write these out. My brackets aren't that good. There we go. So the natural number is less than 7, so we could say 1, 2, 3, 5, and 6, but we're not going to include 7, right? Because it says less than 7, not less than or equal to. So there we go. Alright, but it says write each set in two ways. Okay, so we could also write it in set builder notation. We could say A is the set of elements X such that, so that bar right there means such that, and then now we have to define it, right? Such that X is less than 7, right? These values have to be less than 7, comma, X is natural. Okay? So there's two parts, right? We have to say X has to be less than 7, but also X has to be a natural number. Alright, so these are just two different ways to write the same thing, to write that statement in part A. Alright, so let's try this again, part B. So B, again, are natural numbers that are at least 7. So at least, the phrase at least people kind of confuse sometimes. At least actually is a greater than or equal to statement, right? Because we're saying at least 7. Like if I give you the example of I'm going to give you at least $7, that means I could give you 7 or 8 or 9 or more, right? Okay, so let's write that out. At least 7. So B. So natural numbers that are at least 7. In other words, we're going to start at 7, 8, 9. But then we kind of have a problem, right? I mean, we could keep writing forever and never get to the end of all the natural numbers, right? So like we said before, we'll use the 3 dots to indicate that this set goes on forever. Okay? Alright, second way to write it, as we did with the first one, we could write it in set builder notation. We could say B is the set of elements X such that X is greater than or equal to 7 and X is natural. Alright. There we go. Okay. Next we have relations between sets. So sets X and Y are equal if they contain exactly the same elements. That one's kind of easy, right? Equal means exactly the same. Let's see. Number 2 here, set A is called a subset. So think of that word subset. Sub means below, right? Or smaller than. Excuse me. So A is a subset of B if each element in set A is an element of set B. That's it. As long as each part of A is in B as well, then A is a subset of B, and that's the notation right there. Kind of like a sideways U with one part of the equal sign under it. Okay, so A is a subset of B. If any two sets, let's call them C and D, if sets C and D have no elements in common, they're called disjoint. Right? So the word joint means together. Dis means not, right? So not together. Alright, next example here. So let's see. They're giving some information here. We're saying set A is defined as X such that X is less than or equal to 9 and X is a natural number. So it might be easier to actually write this out, write the elements of this set out, since this is a relatively small set. So the numbers have to be less than or equal to 9, and natural numbers. So remember, natural numbers are 1, 2, 3, 4, whole numbers from 1 to infinity. So we'll write these out. Less than or equal to 9. So 1, 2, 3. I don't know about you, but I really don't want to write all the numbers up to 9, right? So we can do this, comma, dot, 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 comma. Let's do 8, comma, 9. And we're including 9, right? Because it says less than or equal to 9. Okay? So that's what that set looks like. Now, part of this example here, part A. Let's see. So which of the sets A, B, and C are subsets of A? So remember, a set is a subset of another set if all of the elements are in the bigger set, right? So A is the set we're looking at. So is A subset of itself? So I'll put A question mark. Oops, that's a bad question mark. There we go. There we go. Is A subset of itself? Well, go to the definition. Is each element of A in A? Yes, it is, right? So A, yes. So A is a subset of A. What about B? Is B a subset of A? In other words, are the numbers 2, 4, and 6 all in this set right here? We didn't write them all, but yes, they are, right? They are whole numbers that are from 1 to 9. So yes, B is a subset of A. What about set C? Well, 3, 5, and 8 are in A, but 10 is not, right? So C is not a subset of A. Okay? Alright, moving on here. Part B, which pairs of sets are disjoint? In other words, which two sets or any sets have nothing in common? Let me clean this up a little bit here so we can see better. Okay. Right here, look at B and C. 2, 4, 6, but there's no 2, 4, and 6 in C, right? Okay, so B and C are disjoint. They have nothing in common. All right, so if we look, B has elements in A, so A and B are not disjoint, and C has elements in A, so A and C are not disjoint. Okay? All right. Are any of these sets equal? Right? Well, I mean, each set is equal to itself, but that's not what we're asking. But are A, B, or C, are any of those equal to each other? And the answer is no, because they don't have all of the exact same elements in each set. Okay? Moving on here. So when graphing, you're going to need to know all kinds of good terminology and symbology here. So look at this chart. This is a great chart to keep handy. Well, you should learn it, of course, so you know this kind of stuff later on. But right now you have this chart. All right, so first row here. So these are greater than statements, right? So interval notation, we use parentheses for strictly greater than. Means not including that value, right? So it's greater than. And on a graph, the number line graph, these are number line graphs, we would graph it with an open circle going to infinity. Right? Because it's x greater than a. Remember, the open circle means don't include the a value, just as the parentheses means don't include a. Okay? All right, next column here, next row I mean. Notice we use square brackets on a. So square bracket means including a, going up to infinity. So for inequalities, we would say this is x greater than or equal to a, because we are including a. All right, so greater than or equal to. And if we were to graph this on a number line, we would make a solid dot at a, solid dot at a, and an arrow going to the right, meaning it goes on forever. Oops, forgot to write an A there. There we go. Okay. Third row, negative infinity to b. Oh, little note here. If you notice, on all these infinities and negative infinities, we always use parentheses, always use the round brackets. All right, because infinity is a concept, not an actual number. So we can never say we would be including something that isn't an actual number. All right, so next one here, negative infinity to b with round brackets means x is less than b. So strictly less than, not including. So if we were to graph this, we would do open circle because we're not including it. And since it's less than, we draw the arrow to the left. Alright, next one here. Negative infinity to b with a square bracket means we're including b and everything below it. So x is less than or equal to b. So we would draw a solid dot on b, and since it's less than, we go to the left. Right. Next row here, a to b with both parentheses means a less than x, less than b. Another way to say this right here is x is between a and b, but it can't be equal to a or b. Cannot be equal to a or b. All right, and another way to say that here, between a and b, but not including a or b. And if we were to graph this on a number line, open circle at a, open circle at b, and connect them, because we want everything that goes between them. Okay. Next one here. So this is including a, not including b. So we would say a less than or equal to x, less than b. Another way to say that is between a and b, and we can include a, but we will not include b. Okay? So to graph this, it would be, since we're including a, solid dot, we're not including b, so open dot, and connect the two. Alright. Next one here, not including a and including b. So a is less than x, less than or equal to b. So between a and b, including b, but not including a. So this would be open circle at a, closed circle at b, and connect the two. Alright, finally last one here. Square brackets on both a and b. That means that we can include a and b. So a less than or equal to x, less than or equal to b, means between a and b and including a and b. And to draw that on the number line, solid dots at both a and b, and connect. Okay, these are important. This chart right here is very important for you to know. You should know those off the top of your head, so study them good. Alright, next example here. So we're going to use the information we just talked about here. So for each of these, we're going to write the inequality in interval notation and graph it. Okay, so here we go. Remember, less than or equal to symbols means brackets, right? So including -1, including 2. To graph it, we would do solid dot on -1, solid dot on 2, and connect them. Alright. Next one here, 2 less than x less than 4. So the strictly less than symbol means not including those endpoints. So not including 2 to not including 4. So it'd be open circle at 2, open circle at 4, and connect them in between. Alright, part C, -2 less than x less than or equal to 3. So that means not including -2, oops, but we are including 3. Alright, so to graph that, open circle at -2, closed at 3, and there we go. Alright, then part D, x is greater than or equal to 3. So it's or equal to, so we are including 3. And greater than, so we're going to go on to infinity. And remember again, parentheses or round brackets on infinity always. Alright, so if we were to graph this, we would do a solid dot at 3, and then an arrow going to the right forever because it's greater there. Okay. Next thing we'll review a little bit here are polynomials. So for the given polynomial, identify the following. So I'm giving you this polynomial here. Alright? So here's some terms. The constant term. So constant means never changing, right? We notice these three terms here. Remember, so terms are separated by addition and subtraction. Okay, that's an important thing to remember. Terms of a polynomial are separated by addition and subtraction. That's important. Alright, so constant means doesn't change. So we could plug in different x values. The three that I just underlined will change depending on the x value you plug in, right? But no matter what we plug in for x, the negative 3 will never change. So in other words, in a polynomial, the constant term is the term that has no letter with it, no variable. Alright, part B is the leading coefficient. So leading means in front, right? Kind of, but be careful here, right? If you remember back to your algebra days, your high school algebra days, that the largest exponent is the one the one with the highest exponent is the leading term. All right. So the leading coefficient, coefficient's the number in front of the variable. So since 4 is the highest exponent, then 3 is the leading coefficient. The degree is the biggest exponent, right? So it doesn't matter if it's first or last or in the middle. Degree is the highest exponent. Okay? Alright, so example 5. Find the following products. So a product is multiplication. Alright, so a product means multiply. So, if you remember back in high school, when you're multiplying two sets of parentheses like this with two terms in each, there was a little four-letter word we like to use, right? When we do math, it's our favorite four-letter math word. No, not that word. The word you're thinking of is not right. The one we should be talking about is FOIL, right? I know there's other four-letter F words you might say while you're doing your math homework, but this one will say FOIL. FOIL means first, outside, inside, and last, right? Okay, so first, outside, inside, last. So that's what the order we're going to do this in. So first times first, outside times outside, inside times inside, and last term times last term. Okay, so first term times first term is x squared. The outer terms, x times negative 5 is minus 5x. Inside terms, minus 4x. Now be careful on the last times last, because it's negative 4 times negative 5. Negative times negative is positive. Okay? Alright. And then what we always want to do is clean these things up. Combine your like terms, right? So remember, like terms have the same variable. So we've got an x squared. We have some x terms in there. We have a negative 5x and a negative 4x, right? So they're like terms. That means we can add them. So it's negative 9x plus 20. And there you go. There's your answer. Okay? All right. The next few are the same. They're foiling problems. So just remember, first times first, outsides, insides, last, combine your like terms. Okay? So if you FOIL on part B, if you FOIL correctly, you should get 6x squared plus 4x minus 9x minus 6. Then combine your like terms, and don't forget, keep writing equal signs as you write each line of your work. That's important. So combining like terms, 6x squared minus 5x, because we're combining the x's, minus 6. Okay? Alright, next one, part C. So this one says 5x plus 1 inside parentheses squared. Be careful. This is a very, very, very common mistake. What some people will do is they'll square the 1 and square the 5x and say, oh, the answer is 25x squared plus 1, and then the teacher does that and says minus all points, right? Okay, don't do that to yourself. Don't lose those points. When we say parentheses squared, what we have to say is we're taking the parentheses and multiplying by itself. In other words, 5x plus 1 times itself, 5x plus 1. Okay? Alright, so we FOIL again, right? First, outside, inside, last. So we'll get 25x squared plus 5x plus 5x plus 1. Combine your like terms, 25x squared plus 10x plus 1. Okay? Alright, so be careful. Don't fall for that trick. Alright, the next one here, part D. This one should bring back some memories, hopefully good ones, possibly not. This one is, look at the two parentheses. We got 2x and 2x, and we got a 5 and a 5. The only difference between these parentheses is the sign in between, right? So there was a little term we used when we have this situation. It's called difference of squares, or difference of two squares, either way. So what we can do, if you forget the difference of two squares thing, that's fine. You can just FOIL. But what you're going to find out, and let me show you here. If we do first times first, we'll get 4x squared. Outside would be, 10x. Inside would be negative 10x. And the last would be negative 25, right? But look what happens here. We have 10x minus 10x. That's 0. So the answer is 4x squared minus 25. So in this situation, when you have same term, same term, same term, same term, just different signs in between, you can use the shortcut and just simply square the first, right? If we square this, we get 4x squared. Square the last, you get 25, and automatically put a negative sign in between. Alright, so that's the shortcut. Difference of two squares. Okay? Probably going to want to practice those. Alright, some more stuff here. This is another common error type problem that students make. I've seen students do things like, oh, look at that, there's an X on the bottom. So this is what you're not going to do. So don't write this part down. Just look. I'm pretending like I'm making a mistake here. So they say, oh, look at that. Well, I am making a mistake because I can't write. There we go. Well, let's see. X squared over x, right? So that should be 3x minus 4x, which is negative 1x. No, that is not okay. Okay? Don't do that. Make it all disappear, right? Too bad we can't do that in real life. But anyway, what we have to realize here is we have two fractions. We have this one here, and we have this one here. These are two separate fractions. So we're going to rewrite it like this. 3x squared over x minus 4x over x. And there are other ways to do this, and I'll show you in a second. And then let's simplify. Right? So 3x squared divided by x is 3x. 4x over x is 4, in this case minus 4. So that's one way to do it. Another way to do this exact same problem is we could say, well, look at the numerator, look at the top. Okay, the top has an x in common, so we could factor out the x. Okay, So we could say x, 3x minus 4 over x, right? So I just factored an x out of the numerator, out of the top. Well, we know x divided by x is 1, goes away, right? So 3x minus 4, either way, you get the same answer and done correctly. Okay? All right, practice that stuff too. Example 7, just a quick review of graphing points. Remember, when they say graph these points, it's always in the same order, x, y, every time. Oops. It's always x, then y. Okay? All right, so let's graph these. So here, let's say this is A, B, C, and D. Okay, so point A, -3, 2. So that means we go -3 on the x and up 2 on the y. So there you go, there's A. B, let's see, I'm going to draw this one in. We would go 1 on the x, -4 on the y. So there's point B. You don't have to draw those lines, I'm just showing you the process. Point C, we go to 3 on the x, 2 on the y, and there we go, there's that point. And 0, 2. So 0, 2 is a little different. All right, be careful when you see that. So 0 means we don't move anywhere on the x. But then we have to move +2 on the y. So there's point D. Okay? All right, moving on. So that was just some review stuff. Now on to section 1.1, functions and models. So there's our objectives right there. So let's talk about a few definitions. So a function. Now you don't need to memorize the word-for-word definitions. You just have to know how to apply these definitions. Okay? Tests, quizzes, and all that, I do not ask for definitions, but you need to understand the definitions to do the work. All right, so first one, a function. You're going to hear that word, or you probably already heard that word thousands of times in your life. So here we go. A function is a rule or correspondence that assigns to each element of one set, the domain. So remember, the domain is those inputs. We'll talk about that in a second. Exactly one element of a second set, the range. All right, so domain is the input, range is the output. And there we go. We actually have those definitions right there as well, domain and range. So domain, so these are all the same, different definitions for the same exact term. X, so domain means x values. It also means the first element of an ordered pair. An ordered pair is your, like 0, 1, the point. Domain is also the input. Range are the y values, or the second element of the ordered pair, also known as output. Okay? Those are important. These two you should know off the top of your head for the rest of your life, or at least until you're done with math in college. All right, let's see, example 1. Find the domain and range of each. So let's look at the graph here first. So domain, this is how we write it. We'll say D equals, oops, not that, sorry. And we're going to use interval notation to describe this. Let's put some arrows on that graph there. So the domain means x values, all possible x values of this graph. Well, technically speaking, since we have those arrows there, it means the x values go that way forever, but also that way forever, right? The graph is expanding outwards in both directions. So what that means is we can go from -infinity to infinity. Okay? Now remember this shape, right? You know this is a parabola. So just a kind of a shortcut whenever you have a up or down parabola. Okay, this statement does not apply to sideways parabolas. For any up or down parabola, the domain will always, 100% of the time, be -infinity to infinity. Or you could say all real numbers, either way. Okay. Now let's talk about the range. So range means all possible y values. All right, so look at all the possible y values. And for domain and range, we always go smallest to largest, left to right. smallest to largest, left to right. Okay? So what we need to say is, well, what's the smallest value this graph can ever obtain? Well, we have arrows pointing down, right? So that means it goes forever down on the y-axis. So that means negative infinity. But what's the highest possible y value on this graph? Well, we look at the top of the graph, right, the maximum there, and we notice the biggest y value is 1. Now, since there is an actual point up there, we're including 1. Okay? So we're going to use the square bracket on 1 because we're including the y value 1. Alright, so there's your domain and range. Alright, part B. So these are all ordered pairs. So remember, each one is an x, y, etc., right? Whether there's numbers or letters, doesn't matter. X, comma, y, inputs, outputs, domain, range. Okay, so this one's pretty easy. The domain. So we're going to list all the domain values. The first values here. Now, we do not need to put them in order, and we do not repeat repeated values. Right? Notice we have 2 3s in our domain. Alright, so we're just going to say 9, 5. We only need to write 3 one time, and 7. And there we go. There's your domain. There's all the first values, the x values, the inputs. Alright, then the range. Let's see, just look at all the second values, right? So we have 5, B, 0, D, and 19. And there you go. There's your domain and range. Alright, so there's going to be times where you're going to be asked, is this relationship a function or not? They could give you sets like we've got, and you'll see we're going to do different ways to do it, but there could be sets, there could be these arrow diagrams, there could be graphs, there could be equations. There's all kinds of different ways to look at a function. So let's decide whether or not it is a function. Oh, I'm sorry, we should talk about what it means first. A relation is a function if there's no repeated items in the domain. In other words, no repeated x values. Part C, a relation is a function if each input has only one output. Okay, so each x value only gets one y value. And the last one, part D, the graph of the function passes the vertical line test. I'm going to show you that vertical line test in just a second here. Alright, so here, let's look at an example. We're going to use those definitions. So, A. Is this a function? Well, just look at all the x values, the first values. Oh, look at that. We have repeated x values, right? So, not a function. Let's look at B here. Again, just look at the x values. Do we have any repeats? No, no repeats. So yes, this is a function. Sorry, kind of got it squished in there. I'll separate them. Okay, and what kind of math teacher would I be if I wasn't a Star Wars fan, right? So here's a Star Wars question. This is an arrow diagram. These are all your inputs, right? So this is your domain. And these are all your range values. So, if we were to write these out like these guys up here in ordered pairs, what would happen, right? You would notice Han Solo is an input, but he has 2 different outputs, right? So if we wrote it out, it would be Han Solo, comma, rebellion, Han Solo, comma, resistance. Han Solo would be a repeated domain or x value, right? So this is not a function. Alright. Now graphs. Up on part D here for is it a function, we talked about the vertical line test. So remember, vertical means up and down. So the vertical line test tells us if a graph is a function or not. A graph passes the vertical line test if no matter where you put it. So I'm going to draw, I know these aren't perfect vertical lines, but just pretend they're vertical lines. Anywhere I put a vertical line, it doesn't matter. I'm only hitting the graph in one spot each, right? For each one of my vertical lines, I only touch the graph once. If that's the case, then yes, you have a function. Okay? So again, if the vertical line touches the graph only one time, no matter where you put that vertical line, then yes, it's a function. Here's the counter example. I only need to draw one vertical line here, and what happens? I hit the graph twice, right? So if you have one vertical line that touches the graph twice, then the entire then the entire graph is not a function. Okay? All right. Now, part F here. So this is one you may or may not have seen before. Usually we're used to, like y equals something with an x squared on the other side, right? But this time the y is squared. So this is something you're not going to run into all that much unless you move on to calculus and pre-calculus and calculus and beyond. But if you graphed this would be a sideways parabola. In other words, it's going to look like that guy. All right, that's a sideways parabola. Well, we just said that one does not pass the test, does not pass the vertical line test. Okay, so that one is not a function. Alright, let's see. So notation here, this is important. For functions of x, f with a 3 in the parentheses, what does that mean? Right? It means a couple things, right? The way we say it is, so the statement is f of 3, that's how we say it. But what it means is, for an input of 3, in other words, an x value of 3, the output is f of 3. And if we actually had a formula, we'd be able to plug the 3 in and calculate, right? Which is what we're going to do in the next couple examples here. Okay? So there we go. That's what that means. Function notation is extremely important. Trust me on this. In this class, pre-calc, calculus, and beyond. All right, example 3. Complete the function table for the given rule. All right, so what they're saying is, here's the x values, here's the formula, here's the function. Let's do some plug and chug, right? So for an x value of -1, in other words, we're going to calculate what is f of -1. So plug it in. You can use a calculator, of course. We're going to replace all the x's with a -1. If you calculate that out, what do we get? 4 plus 5 is 9. So f of x is 9. Second one, they want f of 0. Well, that's nice. Wherever there's an x, it's automatically a 0, right? I'm going to write it out like this. You don't have to write it like that. I mean, you know anything times 0 is 0, right? So, of course, the answer is 5. And the last one, f of 2. Same thing, we're going to plug a 2 in wherever we see an x. That would be -8 plus 5 should be -3. And there we go. All right. All right, part B here. So this is again important. This is where our function notation comes in handy. So for this first part here, f of x equals -3. Well, it says, find the values of x for which f of x equals -3. So we're going to write for f of x equals -3, comma, x equals, in other words, remember, f of x really means y, right? So for the y value of -3, which is right here, what x value, or in this case, what x values, give you an output of -3. So we're just going to follow -3 here. And we notice right there and right there. And there we go. So if you plug in, if you had the formula for this graph, if you plug in a -5 or a -1, for an inputs, you get an output of -3. Okay? Second part says find f of -2. Well, f of -2 just means for an input of -2. So an x value of -2, which is right here. What's the y value on the graph? Oh, that's pretty easy. It is 0. Okay, so if we had the formula for this graph, plug in a -2, we should get an answer of 0. Okay, function notation, again, is extremely important. Alright, section 1.2, graphs of functions. Alright, so we're going to do a little bit of talking about graphs of functions here. So let's see, first thing we've got is our favorite parabola, right? Remember y equals x squared? You've seen that numerous times in high school and beyond. So y equals x squared just simply means take whatever the x value is, multiply it by itself, and that's your y value. Easy, right? So let's go through that. Let's do the top row first here. So 0 times itself is 0, 1 squared is 1, 2 squared is 4. I should write those out. Let me write these out for you. Just to show you, you don't have to write these out. It's just to show what's happening. 2 squared is 4. Now be careful on this one. -1, notice how I wrote it. -1 in parentheses squared is +1, right? Okay, I'm going to talk about that in a second. Let me do the other one here. So -2 in parentheses squared is +4. So side note here, these are different, right? If we take -3 in parentheses and square it, we get +9. But if I write it like this, -3 with no parentheses squared, you use PEMDAS, right? Remember, PEMDAS means do parentheses first. Well, there's no parentheses here. Exponents next. So 3 times 2, or sorry, 3 to the second power is 9 times the -1. So that's -9. So be careful. All right, parentheses make all the difference. All right. So on the bottom of this chart, we want the point. So in other words, the xy pairs. So here we go. 0, 0, 1, 1, 2, 4, -1, 1, -2, 4. Okay, and then we're going to graph this. So we're going to graph all those points. So 0, 0, 1, 1, -1, 1, 2, 4, -2, 4. All right, and we draw it in. And I know it's kind of tight here, but you got to try to draw these lines slightly curved. Okay, don't draw them straight. They're not straight lines, they're curved lines. And don't forget to put the arrows up at the top like that. Okay, and there we go. We graph this function using a table. Okay. All right, here's a definition. So a complete graph, kind of self-explanatory, I guess, right? A graph that shows the basic shape of the graph and important points, like x and y intercepts and points where the graph turns. Okay? You don't really have to know that, just something to be aware of. Okay. So here's another example, graph by plotting points. So we're going to plug in, right? So we have y equals x cubed minus 3x. So we're going to take all these x values up at the top here and plug them in to the equation. Remember, you're going to plug in wherever you see an x. So I'm going to skip some of the work here, but make sure you know how to do it. We're going to take a -2, plug it into that equation, and strangely enough, you'll get a -2. All right? Take the -1, plug in, we get a 2. Take the 0, plug in, that one's easy, right? There's x's everywhere, so plug in a 0, we get a 0. If you plug in a 1, you get a -2. And if we plug in a 2, we get a 2. Okay, so again, I'm taking those x values at the top there, plugging them into the equation, and getting the y values. So now we create these pairs, these points, these coordinate pairs, -2, -2, -1, 2, 0, 0, 1, -2, and 2, 2. All right, and we're going to plot those points. So let's see. -2, -2, -1, +2, 0, 0, 1, -2, and 2, +2. So it looks kind of weird, right? But what this graph's going to end up looking like is this. So, sorry, I'm not an artist, so my lines may not be perfectly clean, but hopefully you get the picture. There we go. So that's what that graph looks like. Okay? Fun stuff, right? Okay. So graphing on a calculator. Now, I know, well, probably on the first day of class here, not many people may have their calculators. We may all have different types of graphing calculators. And, with the online nature of this course, it's kind of hard, actually impossible for me to go through every type of calculator and show you how to graph. So what I'm going to say is, I know you're not going to like this, but Google it. Okay? And this will not be on tests. I'm not going to say, graph this on your calculator and draw it out if I haven't taught you how to graph on your calculator. That wouldn't be fair. Okay? All right. So Google how to use the graphing calculator and do these things. Just to, especially for those of you going on to pre-calculus, calculus, and beyond, good idea to know how to use those calculators like that. Okay, but not for this class. All right, next example here. All right, so between 1950 and 2008, the percent of the voting population who voted in presidential elections during election years, I mean, isn't that self-explanatory? Oh, I didn't write this problem. Is given by this function here, okay? Where x is the number of years after 1950. So that's important. You've got to read these problems carefully. Whenever you have a word problem of any type in math, read it a couple times. Make sure you know what they're talking about. Okay, in other words, what they're saying is x is the number of years after 1950. So if they said what percent of people voted in 1950, the answer is plug in a 0. Okay? Or not how many, but it's the percentage. All right? So that's important. All right. So part A, what are the values of x that correspond to 1960 and 2008? So again, here's the definition of x. How many years after 1950 is 1960? Well, that one's easy. 1960 means your x value is 10. Okay? 2008, how many years after 1950 is that? Well, from 1950 to 2000 is 50 years, plus 8 more to get to 2008, right? So this one would be x equals 58. Okay? All right. Part B here. Find f of 10. So remember what that means. F of 10 means we're going to replace all the x's in our equation with 10 and calculate. Of course, you can use your calculator on this one, but I'm going to write it out just to show you how it looks. So f of 10 means, or it looks like, 0.0155 times 10 squared minus 1.213 times 10 plus 75.26. All right, so if you punch all that into your calculator and punch it in carefully, make sure you're using PEMDAS and all that. You can type it in exactly how I wrote it with the parentheses and the square up there and all that stuff. It should work. So if you plug that in, you should get 64.68. And of course, this is percent, right? Remember, in word problems, you've got to put units on your answer. All right, and so part B also said find f of 10 and explain its meaning. Well, this just means, let's see, so f of 10, we said right there, x equals 10 was 1960. No, not 1690, 1960. 64.68% of the people voted. And there we go. All right. So always read your questions carefully. Find f of 10 and explain the meaning. You don't want to lose points for not following directions. All right, let's see. Part C. Find the percent of the voting population who voted in 2004 and in 1992. All right, so first thing we need to know, well, what x values are we plugging in here? So 2004 is 54 years after 1950. Remember the definition of x up there. 1992 was 42 years after 1950. Okay, so you're going to do exactly what we just did in part B here, right? But we have different inputs, so you're going to find f of 54. You're going to definitely want to use your calculator on that one. And we also want f of 42. Try it out on your own. Punch it into your calculator. You should get 54.956% on this one and 51.656% on that one. Of course, that's assuming that I did my calculations correctly. Okay, that's it for today. Thank you very much. Obviously, if you have any questions, please contact me through the Canvas inbox anytime. Thank you.